It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good afternoon, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we're going to talk about spectra and polarization. To do this, we're going to look at an applet on FET. Let's see. And what we want to do is talk about what Isaac Newton did back when he was in quarantine in the 1660s. Sleepy time tea. Just give me some energy. Newton wondered about what is it that causes a rainbow to form when white light goes through a prism. This was well known that we would see a rainbow as white light goes through a glass prism. Prior to Isaac Newton, though, it was thought that this prism somehow created the colors of the rainbow. So what Newton did in his house was he drilled a little peephole to allow sunlight to go through it, set up a glass prism on a table, and observed as the rainbow was formed on a wall in his house. Now, one thing that Newton expected to see was a circular shape of a rainbow, but instead he got an oblong picture of the colors of the rainbow. So the first thing he did was kept on making adjustments to see if he could get what he wanted to expect, but throughout time, over the course of multiple trials, he kept on getting the same thing, which was an oblong shape. So what he thought of was, well, I've got the colors of the rainbow, so let's turn on our flashlight. And we could see that we got on the bottom right of this page, Roy G. Biv. So what he thought of doing was taking a second glass prism, and he said, well, if this prism creates color, then if I take a second prism, maybe I could create more color. So he took his prism, put it on the red end of the spectrum to see if he could get more colors. And it turns out he just got a fainter red, but not any more reds or more colors. He's tried the same with the blue end of the spectrum, put a prism in the blue spots, and he thought maybe I'd get more blues or more colors, and all he got was just a fainter blue, but the same one nonetheless. He also questioned whether or not he could recombine the colors back into white light. So he took a prism, put it in front of all the colors, and he was able to get white light again. This led him to deduce that the colors of the rainbow create white light, not the prism creating the colors of the rainbow. So we could say that white light, as well as the colors of the rainbow, are all fundamental colors. Maybe you don't have a glass prism or a pinhole in your house laying around, but perhaps you've seen this in a droplet of oil, the colors of the rainbow, or if you're lucky, maybe you have a sprinkler in your backyard and you're able to see the rainbow through that. I'll link a video below describing seeing a rainbow through the sprinkler. So why don't we go back to our notes, we'll draw a picture and describe what we saw. So we'll draw our glass prism. We're going to use yellow light. Not used to talking. Yellow light to represent our white light going through the prism. And as we saw in the picture, violet light bent the most, and red light bent the least. And then we have everything else in between. So we'll draw orange. Let's add a green and a blue. So we got a Roy G. Biv. And again, we can see that red bends the least. Why don't we put that in words? red bends the least, and violet bent the most. And the reason being is the difference between red light and violet light. If we look at our reference table on the electromagnetic spectrum, we see that the frequency of red light is much smaller, a little bit smaller, than the frequency of violet light. But we'll say because violet has a higher frequency. So the higher the frequency, the more light will bend. And that's a result of the interactions of the light with the prism as it travels through it. So there's going to be a greater amount of interactions with a higher frequency. Okay, so first thing we'll say is that white light is a combination of the colors of the rainbow. And we could say that the colors of the rainbow are fundamental properties of light. Meaning that the prism does not create those colors. So we could say that the colors of the rainbow are separated when light goes through a prism. We'll say white light. And this is called dispersion. And lastly, we'll say that we could determine the color of light based on its frequency. So all color represents, Roy G. Biv, are just frequencies of the electromagnetic spectrum. So color is dependent on frequency. So really, when we see color, all it is our brains just interpreting the frequency of light. If we go back to our reference table, there are other colors that we can't see, and those are all the other frequencies of the electromagnetic spectrum. So gamma rays, ultraviolet, microwaves, radio waves, TV, FM, AM, those are all forms of color, but more specifically, they're light on the electromagnetic spectrum. If we want to determine the color or frequency of light, we can use the formula V equals lambda F, where V is the speed of light, F is the frequency, and lambda, as we saw before, is the wavelength. So all we have to do is isolate the frequency. So let's look at number 1 from your light homework together. What is the frequency of a light wave in a vacuum whose wavelength is 4.1 times 10 to the negative 7 meters? So we'll start with what we're given. Lambda, the wavelength, 4.1 times 10 to the negative 7 meters. We know that it's in a vacuum, so the speed of light is c, which is 3.00 times 10 to the 8th meters per second, and we want to find the frequency. So we'll use our formula V equals lambda F, isolate the frequency, so F is V over lambda, and then plug and chug. 3.00 times 10 to the 8th meters per second, all over 4.1 times 10 to the negative 7 meters. Plug that in our calculators and we get 7.32 times 10 to the 14th hertz. Letter A asks us what is the color of light. So we'll go to our reference table. 7.32 times 10 to the 14th. Let's start with our visible light first. And notice that that number is in between 6.59 and 7.69, which is the color violet. So in this case, this frequency represents violet light. Again, make sure when you're solving for a color, we need to know the frequency of the light first. Okay, let's look at number 3. How long will it take a light wave to travel around the Earth? Hint: use the reference table to find the appropriate info about Earth. Well, let's assume that this air is a vacuum. So they say that the speed of light is 3 times 10 to the 8th meters per second. In order to get the distance around Earth, we need to know its circumference. And the circumference is 2 pi r. So we can look up the radius of Earth in our reference table. It's 6.37 times 10 to the 6th meters. So the radius, 6.37 times 10 to the 6th meters. And our goal is to find the time it takes light to travel around Earth. So I'll use our constant velocity formula. V equals d over t. Isolate the time. So the time is the distance over the velocity. The distance around Earth is the circumference, and the circumference is 2 pi r over v. And lastly, we can just plug and chug. 2 pi times 6.37 times 10 to the 6th meters, all over the speed of light, 3.00 times 10 to the 8th meters per second. And we get in our calculators the speed, or the time it takes to go around Earth, to be 0.13 seconds. The last thing we're going to talk about today is polarized light. If you own a pair of polarized sunglasses, maybe you've noticed that they block out reflected light. So if you're driving your car, it's going to block out the light that's reflected off your dashboard. Or if you're looking at water, it'll block off the light that's reflected off the water. If you don't have polarized sunglasses, we're going to have my hand model show you what happens when you look at a computer screen. Notice in the video that my hand model used his left hand, as when he was using the right hand rule, he lost a finger. But as you're able to see, based on the angle of the polarizer, in some cases no light was allowed through, and in other cases most of the light was allowed through. So what a polarizer does is it blocks out light that's coming from a certain angle. So we can say it's a film that blocks out light which is parallel to the film, blocks out light which is perpendicular to the film, and allows parallel light to go through. So if we want, we could draw a picture, or try and draw a picture as best we can. So let's draw a paralyzer, and what it is, it's going to have tiny horizontal slits which means that if light is traveling in the vertical motion, based on how it's reflected off the surface, it's going to block out that light as it goes through the polarizer and not let it allow through. If we rotated it and the polarizer had vertical slits, the reflected light that's traveling vertically will then be able to go through the polarizer. I hope you enjoyed this video and found it useful. Please like and subscribe on YouTube, and I'll see you next time. See ya!